Good morning, dear friends. So in this particular tutorial, I will explain how to design a building, RCC building of G+4 in SAP 2000. So to design the building under seismic loading as per IS 1893 clause, so it must be analyzed by using a response spectrum analysis. So the clause given in IS 1893 says that if the building is located in seismic zone number 3, 4, 5, and if the number of stories are more than 3, then essentially it must be analyzed first of all using response spectrum analysis, and then it should be designed by using IS 456 recommendations. Now, whatever the building you are seeing on a screen, so this is taken from one of the past literature. Just for your reference, I will show this particular page. So this is the building, already it is modeled. So it is a simple G+3 4 structure RCC building. So column sizes are, it is a 300 by 450. So 300 by 450 are the sizes of the columns and beams. And the different loads mentioned in this list already, it is these loads have been assigned on a model, and the model is ready for the next analysis. So first of all, we'll perform the response spectrum analysis. So to perform response spectrum analysis, so we required some data, that is, we required first of all the site locations. So now this building is situated in seismic zone 4. Then building is resting on medium soil. So this data is also required. Then importance factor is 1. So that is, this is a residential building. And then building frame type, it is a special moment resisting frame. So ductility provision is required, is essential in this. So therefore, it is a type of the frame is SMRF. So these 4 data are required while performing the response spectrum analysis. Okay, then we will move to SAP window. Okay, now first of all, define the response spectrum function. So the command for this is define, and then function, define function and response spectrum. So in this, you just search for, so when you click on the drop down list, so these are the different response spectrums from various codes of the different countries. Okay, search for IS 1893 response spectrum. So this is IS 1893 response spectrum. Okay, then add this particular function. Okay, so click on add the function. Then give some name to this. So give to the name as a IS 1893. IS 1893. So this is the name of the function. Okay, then first seismic zone. So this building is located in seismic zone 4. Then important factor is 1. Soil type. So there are 3 types are there, 1, 2, 3. So this building is a type number 2. Medium soil it is. And it is a special moment resting frame. Therefore, it is a factor is 5. Then default damping ratio. So 0.05. So this response spectrum you are seeing, this is plotted for a damping value 0.05. And these are the spectrum values. These are the spectrum values. So this acceleration values, SA values, these are given in terms of G. Okay, so now this is the, in this way we have to define the function, then say okay. Okay. So the function have been defined, has been defined. Then we'll define the load case, response spectrum load case. Then go for define, then load case, define load case. Okay, so these are the different load cases already have been generated. So in this particular list, there must be response spectrum load case. So since we are defining this as a new case, so therefore go for the first option, add new load case, add new load case. Okay, then we'll perform response spectrum analysis in global X direction as well as global Y direction. So therefore, these 2 load cases will define separately. So first of all, response spectrum in X direction. Response spectrum in X direction, RSPX. Okay, then here load case type. Load case type. So click on a drop down list, and here it is a response spectrum. Here is the response spectrum. Okay, now so now here there are three options we are seeing. That is, it is for directional the combination, and this is a modal combination. So what is the meaning of this? Now see, response spectrum analysis, this is a modal combination based analysis. So in the sense, it estimates the lateral forces in each mode, first mode, second mode, third mode, and then afterward it combines. Okay, it combines the result and it gives the response in that particular direction after combining. Then how it combines the result in different modes. Okay, so for that there are three the rules are there. Okay, these are called as the combination rules. So these rules are also given in IS 1893. So first rule is a SRSS. Okay, square root sum of square method. Second is a complete quadratic method, that is CQC method, and then absolute method is there. Okay, now when to use this particular method? Okay, so in IS 1893 also it is mentioned. Now see, first of all, to see, that is to select one of the method for the combination. So first of all, perform modal analysis. That is we must know the time period of each mode. Time period of each mode, first mode, second mode, third mode. Okay, so if the first mode and second mode time period, first mode and second mode time period, if these are closer, how much closer? That variation in time period between first and second mode is variation is less than 10%, then it is called as a closely spaced mode. Again, mode number 2 and 3, you just see the variation in time period. So if it is a variation is less than 10%, it is called as a closely spaced mode. Okay, then so therefore similarly in so if the closely spaced modes are there, then the results accurately we will get from CQC method. So this is given in IS 1893. And if the modes are well separated, that is variation in time period is more than 10%, then the results or the modal results are combined by using SRSS method. That is the second. And sometimes there are some structures that that is some modes, few modes are closer and few modes are well separated. Okay, so then in that case, go for the absolute. Now for this model, for this particular model, actually the modes are well separated. That is, time period of the different modes variation is more than 10%. Afterwards I will show the results, model results also. And therefore we will use for the combination of the results in different modes, we will use SRSS. Here also we'll use the SRSS. So just click on SRSS. Here also click on SRSS. And then, since as already I mentioned that this is response spectrum is a modal combination based method, so therefore it requires the result from the modal analysis. Okay, so here there is a default model, it is true and correct. Okay, then come to this particular table. Okay, now here acceleration. Now we are defining the load case in X direction, so here must be U1. When we are performing in Y direction, here must be U2. Okay, now here U1 IS 1893. Now the scale factor, how much it should be? It must be 9.81. Why it is 9.81? Because while defining the response spectrum function, just I was told that, so that is all the spectral acceleration values are given in terms of G. Okay, so in terms of G. So therefore, to convert the G value into acceleration, meter per second square, so therefore multiplied by 9.81 and add this. Okay, so this is the part. Now, okay, so this is the all part is completed. Say okay. Now we have defined the response spectrum load case in X direction. Similarly in the Y direction. Okay. Now, whatever the case defined, RSPX, same case, first of all, copy. So therefore, go for second option, add copy of the load case. Copy of the load case. And here, for Y direction, whatever the necessary changes, for example, load case name is RSP Y, then here all are the same. Only thing here, in this table, it must be U2. And this modify, just modify. Okay, so this is the only change. Okay, and then say rest of the things are same as the in X direction. Say okay. Okay, now we have defined the RSPX and RSPY. Okay, then just we'll perform this modal analysis. I will show whether the modes are well separated or not. So therefore, we'll run the analysis. So not necessary, we'll perform only, we will run only the modal load case. Okay, so the analysis is over. Now see, go for display, show table. Show table, then it is a structure output. Now we'll see only the modal informations. Okay, we'll see only this modal information. Okay, and then say okay. So we'll get the results in table forms. So go for say second modal. Okay, we'll see this particular table. Okay, now in this, now this is a mode number 1, 2, 3, 4, 5 mode number, and these are the time period. So what is the time period for the first mode? 0.53. Second mode, it is a 0.49. The variation is 10% or more than 10%, right? So therefore 1 and 2 are well separated. Then 2 and 3, again see what is the variation. This is 0.49, 0.41. Again, there is a variation more than 10%. Then this mode and this mode, again, variation is more than 10%. So therefore, whatever the structure we are designing, the modes are well separated, and therefore, for modal combination, we have selected SRSS method. Yes. Then we'll unlock the model. Okay. Now, response spectrum load case already we have defined. Now, in IS 1893, there is one clause is given regarding the design of the building. So the clause is here, this particular clause. Okay, in detail, this particular clause I will explain later on. So this is clause number 7.8.2. Now, while designing the building for a seismic loading, the minimum base shear, it should be designed for a minimum base shear equal to the base shear in the fundamental mode using equivalent static load method. That is, in the equivalent static load method, in X direction or in Y direction, whatever the base shear in first mode. So the building should be designed at least for that much base shear value. So this is it is said in the clause number 7.8.2. So therefore, and now while performing the response spectrum analysis, parallelly or simultaneously, it is also required to perform the equivalent static load method, and it is required to calculate the base shear in the fundamental mode using equivalent static load method. Now, to calculate the base shear using equivalent static load method, we have to use the equation for time period given in IS code, because here it is mentioned, that is, calculate the time period by using as per the clause 7.6. Okay, so what is where it is 7.6? Okay, so these are the equations given. Okay, so the three equations are given to calculate the time periods. Now we'll use this equation to calculate the time period. So using this time period, estimate the base shear using equivalent static load method, and the building should be designed at least for minimum base shear equal to this. Okay, now this is the clause I have just shown. Okay, more detail I will explain the clause as per the this thing. as the analysis proceed. Okay. Now we'll define the equivalent load case. Okay. We'll define the equivalent load case. Then define how to define the equivalent load case. Define, then go into load pattern. Okay. Go into load pattern. Okay. Now here. Now first is, now this equivalent load, equivalent static load also will perform in X direction, also in Y direction. So first is EQ equivalent load case in X direction. Okay, so it is a, then type, it is a quake load. It is a quake load. Okay, and here select our code, IS 1893-2016 is the code, and just add this. Okay, similarly, EQY, it is a quake load, IS 183, add this. Okay, again we'll modify this particular case. Now select first EQX and click here, modified lateral load pattern. Modified lateral load pattern. Okay, what the modification is, now this is EQX. So therefore, first is, here must be global X direction. Now this is the zone factor. Now this given building is situated in zone 4. So Z value is 0.24, right? Soil type, it is by default, it is 2, it is correct. The important factor is 1, it is also correct. Response reduction factor is also 5, okay. Now, the time period, this is most important. That time period we have to calculate using the equation given in IS 1893. So here we have to choose this particular option. We have to choose this particular option, that is user defined, and just click on user defined and calculate the time period. Now how much, what is the equation given? The equation given is, okay, equation given is 0.09 under root of D, 0.09 divided by under root of D. Okay, so here, this is the building, this is our building in plan. Okay, so this is Y direction, this is X direction. Now time period by using that equation is already calculated. So 0. In X direction, it is 0.09 divided by under root of D. D in the sense, in X direction, this dimension is 15 is the dimension D as per the definition IS 1893, and along Y direction, the dimension for D is 8 meter. So substitute in that equation, we'll get time period in X direction 0.03. Okay, so therefore in SAT, we'll go for user defined, and it is 0.023 in X direction. 0.023 is the time period. Okay, and say okay. Okay, then Y direction also we will modify this. So modify lateral this thing. So here now it is global Y direction. Here must be global Y direction. Zone factor must be 0.24. Rest of the thing, this is okay. Now here it is user defined value. Now in the Y direction, what is time period? 0.031. It is 0.031. 0.031. So these are the time periods using IS 1893 equation. Okay. Now we have defined both the load patterns for equivalent static analysis. Okay. Then now we'll run the analysis. Okay. So we have defined EQS, EQY in load pattern. Therefore, automatically it generates here. Okay, so this is EQX load case and EQY load case. So in SAP 2000, this is the beauty. So already, if the case is defined, any load pattern, load type is defined in load pattern, automatically the case generates here. Okay, so then run now. Now, first of all, we'll see only the base shear values. Okay, base shear values. Then display show table. Okay, so show table. So at the end here, structure output. Only we require the base shear values, right? Only we require the base shear values. Then for load, which load case? Select a load case here. Select load case. Okay, so only EQX, EQY, and response spectrum, RSPX and RSPY. Okay, so only we'll see the base shear values for these 4 cases. Okay, very information is there. Okay, so for response spectrum analysis in X direction, what is base shear? 198. Okay, while as in equivalent static load method, what is the base shear? 2 how much? 243. 243. So this is by equivalent static load method. So what that particular clause says, okay, so the building should be designed for at least base shear equal to whatever the base shear in the fundamental mode by equivalent static load method. So we have to design the building in X direction for base shear equal to this much. But response factor, how much it is coming? 198. So actually this 198 here, how much value should come? Must be here. It must be 243. So what is the scale factor required? So scale factor in X direction will be, okay, so scale factor in X direction required will be equal to 243, okay, 243 divided by 243.198 more correctly, divided by 198. Okay, this is the shear scale factor. So how much answer is coming? So it is 243 divided by 198. 198. So how much coming? It is 1.22. Okay, it is 1.22. It is 1.22. So this is the scale factor in X direction. Okay, then what is the scale factor in Y direction now? Okay, so by using response spectrum, what is the base shear in Y direction? 197. And by using equivalent static, how much it is? 243. So in Y direction, the scale factor will be equal to, now directly we'll do into the calculator. So how much? 243 divided by 197. 197. How much it is? Again, it is near same. 1.23 is there. Okay, it is a 1.23 or 1.22. That is same scale factor is required in X direction as well as in Y direction. Okay, so this is actually the clause. Okay, now we will apply this scale factor. Now where to apply? Just I will show. Say okay, done. Then again unlock the model. Unlock the model. Okay, then again define load case now. Okay, define load case. Then the response spectrum load case. Define, that is response spectrum load case. Just modify this. Okay, now what is the scale factor here? How much it is? Scale factor is 9.81. So you just multiply to this value, okay, by 1.23 and just modify. Okay, this is in X direction. Similarly, in Y direction, the same scale factor is there. Modified load case, you just multiply here by the same scale factor. It is 23, and this modify. Okay, okay, and again we'll run the analysis. Analysis over. Again we'll check the base shear values. Okay, now response spectrum. See, by using response spectrum, what is the base shear is 2.243, and by equivalent static again it is 243. Now they are matching. Okay, correct. So then in Y direction, what is scale factor? 243. Base shear is 243, and in using RSP response spectrum, how much it is? 243. Okay, now we will carry out the design. So this is the meaning of this particular clause. I repeat the clause. The clause says that while designing the building, it should be designed for a minimum base shear equal to the base shear in the fundamental mode by equivalent static load method. That is, we have to design the building for these values in x direction. In this is the minimum base shear values, and therefore we have scaled up the base shear values in by response spectrum method, response spectrum analysis in x and y direction. So in this way, the scaling up should be done. Okay. Now analysis part is over. Okay, analysis part is over, and we have matched the base shear values. Now next is the design. Okay, next is the design. Okay, so design, it is very simple. So here there is a command, say design command. You just click on the design. Then it is a concrete frame design. Okay, it is a concrete frame design. And first of all, click on the first view, revise references. Okay, then here you just select our code, Indian code, IS 456. So design will be, so these many codes are available in SAP 2000 library. So we can design by any the foreign the codes also. Now we'll select by IS 456 2000. So once it is selected, this particular the code, then automatically in this code the different load combinations are given. So SAP 2000 automatically give the results by taking the load combination from that, this particular the code. Then say okay. Okay, now just I will show what are the different load combinations have been generated. So select a design load combinations. Okay, so we can see from here also load combinations. So it is defined and it is a load combinations. Okay, load combination. So here also we can define the user, that is apart from the code load combination. Suppose any user want to specify his own this thing load combination. So he can assign through this by using this particular command also. Add and from this. Okay, so here already, since we are carrying the design using IS 456, not necessary to design the load combination separately. I will show the generated load combinations. Okay, so first of all, we'll complete the design part, then concrete frame design, then select the design combination and go for third, start design checking of the structure. Now the designing part is going on. Yes, now design has been completed. Okay, now this is a on screen, you are seeing some values. So these are nothing but what here it is a longitudinal reinforcement. So these are the longitudinal reinforcements in meter square. So in the column it is 2000 millimeter square. 2000 millimeter square are the reinforcement area required under different critical load combinations. Okay, so once we suppose click on this thing, any member. So it is so this is okay. So it is showing the load combination number 20. Okay, so this is a given this thing, the area of the reinforcement for combination 20. The location is 5. That is on a beam. The software automatically divides into different segments, and so it is displaying the reinforcement at a different segments. So at the edge, at the center, and near to the right edge. Okay, then this is the top steel, this is the bottom steel, and this is the shear reinforcement. Okay, I will show this in table forms also. So these are the reinforcement. Now next is, interestingly, I want to show one more point, that is design. Go for design, concrete frame design. And here one option is that display design informations. Okay, so first of all, so that is, it is showing the some reinforcement area that is there, but whether the design is safe or it is unsafe. So that first of all we'll check, we'll see. So go for here, display design information, display design information. Okay, so here there is one this thing. So click on a drop down list. So on this particular figure on a screen, we can display the rebar percentage. Now this is, what is this? This is reinforcement in terms of longitudinal reinforcement in terms of area. Then we can display this in terms of rebar percentage. Then shear reinforcement also we can show. Then column PM interaction ratio also we can say, and all this. Okay, so and it also shows the different types of the failures. Okay, different types of the failures are, so it is showing here. Okay, first is joints. First is identify PMM failure. That is column. We know the column we are designing for axial load plus biaxial bending. So if suppose any column fails under PMM interaction, PMM action, then immediately it will display on that particular column. Then identify shear failure. The columns and beam, these are the flexural elements. So it may fails under shear also. So any member fails under shear, then on that element, the V later comes. If the V later comes, it means that that particular element fails under the shear. On a column, suppose V is also there, display is V as well as PMM. It means that column fails under PMM as well as the V. And combinedly, identify all failures here. When I click on this, I want to see all type of the failures at once. So click on this and say okay. Okay, and just I will see the 3D view. Okay, now here, are we seeing on this particular figure, the 3D, anywhere, are we seeing any PMM letter anywhere in this? No. So that is all the columns are safe for PMM action. Okay, so that is sizes and whatever the reinforcement initially defined while assigning the member that column, whatever the initial reinforcement. So for that, it is safe. Second, on the different elements, column and beam, any letter V is there? No. So that is all the members, column and beams are safe for shear. Then on these columns and beam, anywhere there is a letter of BCC, capital BCC, that is beam column capacity. In IS 1893 design philosophy, it should be a strong column and weak beam. So on a column, or in beam, on a beam, suppose the letter comes as a BCC, it means that the beam capacity is more than column. It indicates that this is also one type of failure. And so if BCC letter comes, it means that the beam moment carrying capacity is more than column. So in that case, this is also not acceptable. Okay, so therefore, that is also supposed to be one type of the failure, and it is required to redesign it. So that is third type of failure. So these are the different types of the failures it is showing. So, but if you see on the 3D this thing, the 3D building, whatever the figure here, anywhere any letter has not come. Okay, so it means that the design completely is safe for all actions. That is one thing. And here one status bar is also given. Status bar is also given. So the dark line, dark shade, it indicates that this is highly stressed. It shows the stress level in that particular element. So these are some beams we are seeing, it is very highly stressed, but they are safe. They are safe, but highly stressed. And column, but in this thing, the beams at the lower level, they are very gray. That is, they are not that much stressed. So this is the meaning of this status bar. Then also we can see the design results. one more check is also there. Verify analysis versus design. And next is verify all members passed. When we click on this, any message comes, yes, all concrete frame pass the stress capacity check. Okay, so the design is safe. That is, it is passed the stress to capacity check. Okay, so stress also okay, capacity is also okay. Then next is a design, then concrete frame design, then verify analysis versus design results. Okay, the message is that so it is analysis and design section match for all the concrete frames. Okay, so that is also a safe message, safe design message is there. Okay, that is the next one. Then also we can see the different results. So about the so just see, initially before to start the design, we have selected the code IS 456 code, and in that the different load combinations given. So only the user have to select the code. Automatically the SAP 2000 takes the whatever the load combinations from the respective codes, and these are the load combination automatically generated. Okay, so these are automatically, so it is near about I think 1 to 20 code, this thing load combinations are there, generated load combinations. Okay, so it is automatically generated. Okay, then also can we see the load combination? Just I will check. Okay, see, now as I said, that is whatever the different load combination automatically generated, we can see from this also. So define, and here it is load combinations, here load combinations. Okay, so suppose I want to see what is this load combinations, design combination 16. So just select that and modify show load combination. Okay, so this is which what is load combination? It is live load floor, that is 1.2 live load floor plus 1.2 response spectrum y direction. Okay, this is the load combination. Similarly, suppose load combination 10, modify this. So it is 1.5 linear static equal this thing EQY 1.5 EQY. No, it is a this thing highlighted in this. So it is only 1.5 EQY, 1.5 EQY. This is the load combination. Okay, so these are the different generated load combinations. So I want to just see that, tell you that, so user need not necessarily to define separately. Automatically it takes this thing. Then about the reinforcement details of this thing. So display, no, design results we can see here only. So for example, XZ code, this thing. So just right click on the member, right click on the member. When you click on the right click, then so this actually the SAP 2000 carry out all the check all the combinations. Okay, and the critical combination for this member is combination number 13. Okay, so this is so longitudinal reinforcement in meter square is equals to this much, 2000. Then measure shear, measure this thing. Then this is the summary. When you click on the summary, so it will give the summary, that is in measure what is the movement is there, what is the factor movement, what is the shear force in V2, V3 direction. Okay, so all these details about the design it gives here. Okay, so that is you just click here. Then flexural details you just click here. Okay, so that is some important equation. So this is as per IS 456. Then suppose shear details for this. Okay, so you just click here, how the values comes. Okay, so these are the ASV divided by spacing. It gives ASV divided by spacing. So this ratio is equals to this much, 3.3 into 10 to the power minus 4. So since the our unit is meter, therefore these values are seems to be very less, but we can calculate the spacing from this particular equation. So that is, this is ASV divided by spacing equal to this much. So from that we can calculate the spacing, yes, in millimeter. So it may comes to 100 millimeter or like this. Then interaction. Okay, so for this, what is the interaction curve? Also this show. So it is PMM interaction curve. So this is P value, moment value 3 direction, moment value in 2 direction, M22. Also joint shear. Okay, so at that particular joint, it gives the details. Then BCC, beam column details. Okay, beam column details. Okay. So how this is, that is beam column capacity, the check is carried out. So you'll find the details here. Okay, then tabular result. If we click on the tabular result, so this is the size of the column. Okay, size of the column is 300 by 450. It is a column design status, no message is there. So that means design is safe. And this is PMM. Okay, these are the different load combinations. And the reinforcement, it gives the reinforcement at different locations. Okay, so this much. So after clicking on any member, we can see the details of all the details, design details of that particular element. All right, okay. Then also we can generate the report. So if we click on the file, then a report setup, create a report. You can click a report here, then whatever the complete analysis, whichever we have carried out, response spectrum analysis, equivalent static load analysis, then matching of the base shear and all this, and the design procedure, load combination, everything. So we'll get a brief report of this design of this RCC building from here. So it will be, we'll get a report in the PDF format.